Okay, good afternoon. My name is Jeha. So I'm currently the automation manager at Jindo AI. So my background is a little bit unique. So while I originally trained in architecture, so all the way through my postgraduate studies, I leveraged that foundation to transition a little bit into architecture and computing, which led me to my previous role as the policy lead at UCL, where I also published several papers. Now I focus on driving efficiency and innovation through automation. Now, some of you might have seen me yesterday presenting with Andrew Lau about using AI to rapidly design and fabricate functional walking robots from NLP, natural language descriptions. But however, today I'll be presenting my thesis, Modeling Edge Computing Dynamics for Smart Cities, a comparative study between Markov chains and Bayesian networks in Barcelona. So this research explores how we can move beyond static planning to deploy the next generation of digital infrastructure in complex urban environments. Let's see. Oh, there we go. Okay. So our agenda for the next 20 minutes is pretty straightforward. So we'll start by defining the smart city challenge and the rationale for this research, culminating in our hypothesis. Then we'll dive into the methodology, which is built around agent-based modeling and the two stochastic models I compared. And then finally, we'll review the simulation results and discuss the conclusion for future urban planning. So smart cities promise incredible efficiency, but they also face a critical bottleneck. So as billions of IoT devices, sensors, and autonomous vehicles connect to the network, we generate enormous amounts of data. So sending all that data to a centralized cloud miles away creates two fatal problems. The first includes high latency, which is unacceptable for real-time applications like self-driving cars, and massive network traffic. Now, the proven solution is edge computing, so processing data at the edge of the network closer to the source. But this also introduces the challenge: where exactly do you place these edge nodes in a complex city like Barcelona? Now, they need to be somewhere where the users are, but they also need stable energy, minimal latency, and balanced workloads. Essentially, traditional planning simply can't handle this complexity and dynamism. So, our current infrastructure planning relies heavily on static models or simple heuristics. Now, these methods fail to capture the dynamic and stochastic nature of urban life, the random, unpredictable movement of people, data, and energy demands. Now, this is where agent based modeling, or ABM, comes in. So, ABM allows us to simulate individual agents, our users, interacting with a spatially explicit environment, a digital twin of Barcelona built with real geospatial data. Now, this gives us the complexity that we need. Now, the novelty of this research is comparing two powerful models within that ABM framework to find the best predictive tool for optimizations, namely Markov chains versus Bayesian networks. Now, the hypothesis that I formulated was that the Bayesian network model will be more effective than Markov chain model at optimizing deployment of edge computing infrastructure. And this is namely due to the Bayesian network being specifically designed to model complex interdependencies and uncertainty. Now, an optimal site isn't just about user density, it's about user density and energy grid, load, and current traffic all at once. Now, this multivariable challenge is exactly what Bayesian networks are built to solve. So if I show you the methodology overview, I developed a simulation using ABM framework in MATLAB, setting Barcelona as a case study due to its complex urban structure and open data availability. Now, the simulation was built on a 100-meter by 100-meter resolution grid, which was populated with agents whose behavior was driven by real-world input data. A land use map showed where agents gathered, and energy consumption data showed resource availability for our simulated edge nodes. Now, the final objective was to find the set of locations that resulted in the lowest network latency and the highest load balance across the system. Now, let's take a look at how we applied the two models. So first, the Markov chains. Um, the Markov chain models a sequential movement. So the probability of an agent's next location depends only on its current location. Hence, it's memoryless. We use this to model the long-term steady-state distribution of agent behavior. Now, This gives us a good estimate of the average user density over a long period, and it's pretty effective for general predictable trends. Second, the Bayesian network models probabilistic relationships as a graph. It allows us to define direct and indirect dependencies. For example, we can calculate the probability of an optimal site being chosen, given factors like user density, energy load, and data traffic simultaneously. Now, this ability to integrate multiple conditional variables is what makes it theoretically superior for complex event-driven scenarios. So the implementation of the Bayesian network was the most complex part of the simulation. So here you see a snapshot of the code that I used to integrate the Bayesian network. Now, the critical steps were implementing the directed acyclic graph, a DAG structure, to define the cause and effect dependencies and setting up the conditional probability tables, CPTs, that ingest the real world data, such as our energy consumption file. This entire structure allows the network to continuously recalculate the optimal site in real time based on the current state of all interdependent variables. In comparison, the Markov chain implementation focused on solving for the transition matrix and finding its long-term steady-state solution. Now, this code essentially calculates the long-term probability of an agent being in any specific 100-meter grid square. Now, while this provides a very useful long-term distribution of user density, or the average state, it lacks the capability to factor in non-sequential events such as the localized power failure or a sudden traffic surge, which are crucial for real-time edge node optimization. Now, the first major sprint focused on establishing our base model. So this visualization shows the output of the Markov chain model and the Bayesian network model, essentially giving us a high-level predictable map of user density based on the steady-state distribution. So in this sprint, the objective was to successfully implement the two chosen stochastic behavioral models within a grid consisting of 4 land use quadrants. So the top left being residential, top right being commercial, bottom left being industrial, and bottom right being other or undeveloped. So if we deployed our edge nodes based only on this map, we would minimize the average distance to a user, but we would risk serious overload during peak demand because it doesn't really account for the current resource limits or network capacity. Now, in Sprint 3, I finalized the integration of the Bayesian network model. So this visualization shows the final optimized placement of edge nodes as determined by the Bayesian network model and then the Markov chain model. Notice the subtle but critical difference in placement. So the Bayesian network has strategically located nodes not just in highest density areas, but also slightly outside them to ensure better load balance. Now, our final metric focused on the standard deviation of the workload. A lower standard deviation means better load distribution. The Bayesian network placements achieved a significantly lower standard deviation. Now, the results confirmed our hypothesis. So the Bayesian network model significantly outperformed the Markov chain across all key evaluation categories. Specifically, the Bayesian network solution delivers superior performance in 2 areas. First, a lower overall network latency, and second, a far more effective load balance. The Bayesian network's ability to factor in resource constraints like the real-time energy availability alongside user demand allowed it to find placements that were not only close to the users, but were also robust and resilient. Now, this key insight validates the need for probabilistic modeling for uncertainty in urban planning. Now, the Markov chain, constrained by its focus on sequential states, simply couldn't compete with the Bayesian network's ability to model complex simultaneous interdependencies. So, this research has 2 major implications. So first, it strongly validates the agent-based modeling framework as the ideal tool for modeling the dynamics of urban digital infrastructure. Now, by integrating geospatial data with stochastic behavior, we can now simulate urban systems with unprecedented fidelity, moving beyond simple heuristics. Now, second, by successfully optimizing edge computing infrastructure, this work directly contributes to sustainable urban development. Now, optimized infrastructure uses less power, handles traffic more efficiently, and allows for seamless integration of resource-intensive smart city technologies, which themselves support sustainability efforts. Now, In summary, this thesis successfully compared two stochastic models within an ABM of edge computing in Barcelona. Now, we confirmed that the Bayesian network is the superior, more robust, and more effective optimization tool. Now, for future work, there's quite a few things that we need to consider: looking into hybrid models, implementing real-time data more efficiently, cross-city validation, and implementing values for interpretability. However, the next two critical steps that I'm going to be tackling immediately is looking into the following. So we need to incorporate even more detailed empirical data, such as actual computing logs and specific traffic patterns to further ground the model in real world performance. Now, currently, I am working with the city of Barcelona and key IoT service providers in Barcelona to source hourly updated zoning and building permit logs, as well as mobile network CDR and Wi-Fi probe data, as well as smart meter energy readings. And secondly, we need to expand the current scoring metrics to enhance the model's generalizability, ensuring this powerful tool can be applied effectively to other global cities with varying urban structures and data landscapes. Um, so this slide sort of lists all the key references and data sets that underpin this research. I'm happy to provide a complete list to anyone who's interested. Um, and yeah, that's pretty much it. Thank you so much for listening. I'm happy to take any questions. And if you guys want to contact me as well, this is my email. But yeah, thank you so much.